what I wanted to share with you is there's a database called DynamoDB, and quite a common thing with DynamoDB is you want to batch write an item. Some items can get rejected. Basically, what you need to do is retry it, but it requires that you retry it with with exponential backoff. So what it will do, it will give you some unprocessed items. A map of tables requests against us were not processed. If DynamoDB returns any unprocessed items, you should retry the batch operation on those items. However, we strongly recommend that you use an exponential backoff algorithm. If you retry the batch immediately, the underlying read or write requests still fail, etc. The idea here is we need an algorithm which does batch put with retry. Yeah, we want to write some algorithm. So what we can do is we have some items, which is like an array of anything, let's say. While items dot length.
Yeah.
Await. There's some function here which is like batch put. Something like this, right? It's some async function up here. And we do db.batch put with the items, which takes items any. And what we do is unprocessed. We take the response, and if it's unprocessed, then items equals unprocessed. And now to add the exponential backoff, that's obviously quite a trivial example, but that's the general idea. Now to add the exponential backoff, we have to do some sleep. So let's create a sleep function, which is new promise bar set timeout b, which takes a duration to wait and waits for that amount of time.
Okay.
Makes sense?
Yeah.
So what we could do is we could just, before going to the next one, we await sleep for 10 milliseconds. Now, exponential backoff says that you know, we should change it in an exponential way each time. So it starts at 10. But then after each one of these, duration should be modified to be 1.5 times the duration, let's say. So let's call this F, let's call it P, which is the factor. Okay, fine, let's call it the factor.
Okay.
Theta. Nice.
If this is exponential, it shouldn't be multiplied by the duration itself several times.
Sorry, it should be. or it shouldn't be. What are you saying?
When you do exponential multiplying, you shouldn't multiply by duration itself several times, or 2, 3, and so on, depending on the iteration of your loop. It's not that?
No, exponential is that it's multiplied by itself.
Yeah, exactly.
Well, it is multiplied by itself. Duration is multiplied. Sorry. It's still multiplied by itself. It's still exponential. What you're saying is duration should grow by this amount. Is that what you're saying?
Yeah, kind of.
Kind of. What's different?
You should actually you are multiplying twice on this example, right? Okay,
Yeah.
it is exactly that, actually.
Yeah. You know what? I might turn this into JavaScript just so that we can run the file.
Actually,
no, let's just not run the file and keep it in TypeScript. But yeah, the idea is this is wrong, Jay. That's a myth.
I just sent you a math exp. This is what I was thinking about.
So
yeah.
Okay, well, there's math.exp and there's math.power.
Yeah.
Right? And they're two different things. So what do you think math.exp does?
Okay. It's actually power, not exp.
You were thinking of power, right?
Yeah, exactly.
Okay. First of all, power series is different to math.pow. Math.pow is not equivalent to exponential. Exponential is the same as coronavirus. If the factor of growth from the previous step is greater than 1, then the growth is exponential.
Okay. Yeah,
if
you're
the
right.
growth factor is greater than 1, i.e. this theta is greater than 1, then it's exponential. As long as this is, even if this is 1.01 or 1.0001, that's still an exponential growth because it's still compounding to the previous step.
Yeah, you're right.
So but it's good to challenge this, and there is like some confusion here. E to the x, e is actually a constant.
Yeah, I just saw that.
And math.pow we'll do like we'll do like 2 to the 4, which is very different to compound growth. Anyway, so what we want to know is this.
Okay.
This is exponential backoff.
Now I got it.
Yeah, this is exponential backoff. So what's it? Duplicate function. Strange. Okay, batch put with retry. So this is what we want to do. Now the thing is, if we start at 10, we don't want this to run forever, this code, right? There's some limit. So if we say, okay, how many times do we want to try to do this before we give up? Let's say 100. Right?
Yeah.
So what we do is we say, well, I and I plus is less than 100. Let's say limit.
Yeah.
Yeah.
Okay.
And let's actually call limit n. Now the question is, how long, let's say that it does fail every time and we still have unprocessed items. What is the maximum amount of time that it will take batch put with retry to run in?
Okay. Duration multiplied by theta multiplied by n.
Yeah.
Basically.
Yeah. So I need to find some fresh paper that I can use. So right now I do not have any. So how long will this take to run this function? Let's say that the batch put is like 1 millisecond.
Sorry?
Let's say that the batch put takes 1 millisecond to occur. How long will the entire function maximum take to run? What's the maximum time t that it will take?
Sorry, your audio is not that good.
I know why. Hold on. Better?
Yeah, much better.
Okay, so so the question is, how long will it take for this batch put function to run?
Okay.
Total
Actually,
time.
yeah, it's the duration multiplied by theta multiplied by n plus batch put with retry itself runtime.
Okay. So I'm pretty sure what you said is wrong, but let's get into it.
Okay.
So just to be clear what we're trying to time here, I'll write the code for how we would time it. So what we could also do, of course, is we could have let start equal date dot now, and then we could have elapsed equals date dot now minus start, and then if elapsed greater than, whatever, let's say 10 seconds, then return, or something like that.
Okay, so not took more than 10 seconds.
Yeah, but we don't know. So this is one way, and we can time how long it took. And we could also, at the end of this, just return date.now minus start to see how long it took. But, we need to know actually how long this will take if we limit it by 100. Or at least let's go with that example. To limit it by steps, how would we calculate this? So what did you say exactly? What was it? What was your formula?
Okay.
For this elapsed thing here?
Yeah, okay. You will actually sum all the duration that you put on sleep.
You will sum all the durations
that you put on sleep plus the function itself execution time.
If you were to write a formula, what would the formula be?
On code is easier because you can just keep a variable and is summing up. Multiply that result duration. Actually, the multiplication theta multiply duration.
So here we have theta.
Okay, the duration is multiplied is different every time, every loop. So
Exactly.
we
Exactly.
can't use duration.
Yeah. So if we say A0 is, can you read this, or is it too small?
Yeah, I can.
Yeah. So A0 is gonna take time duration, right?
Yeah.
So that's cool. Let's say that D is 10, theta is equal to 1.5,
Yeah.
N is equal to 100.
Yeah. Okay.
When A is 0, D will be 10. When A is 1,
It will be
D will
10 multiply 1.5 multiplied by theta.
10 multiply 1.5, or in other words, A0 dot 1.5.
Yeah.
A2 is going to be A1 multiplied by 1.5, which is 10 multiplied by 1.5 multiplied by 1.5. A3
and so on.
is going to be
Basically the same
10
thing.
multiplied by 1.5 multiplied by 1.5 multiplied by 1.5, which is, A2 multiplied by 1.5. This here comes out as 10 multiplied by 1.5 cubed, right? This is 10 multiplied by 1.5 squared. This is 10 multiplied by 1.5 to the 1. And this is 10 multiplied by 1.5 to the 0, right? Which is the same, by the way, as d theta, 0. And what we want is the sum of all of these, right?
Yeah, I'm not sure if this is actually 10 multiplied by 1.53, for example, because you will do 1.53 first and then multiply by 10. It's not that?
Yeah, but you have, so let me break this out for you. I'll do this again. So it's, you have the starting one, which is 10 multiplied by 1.5, correct?
Yeah.
And then you multiply this multiplied by 1.5. Yeah, but it doesn't actually matter that this one is in brackets, because multiplication is an operation in maths, which is the word commutative or transitive? I can't remember, but it basically means it doesn't matter where you put the brackets. So 10 multiplied by 1.5 times 1.5 is the same as if I do like this. This is the same as d multiplied by theta multiplied by theta, which is what? D theta squared.
Okay.
Are you not convinced?
Yeah, I'm not sure. Let me choose. Yeah, is that correct?
Do you want to do an example?
Yeah, I just did.
Okay, so you agree with me now.
Okay, that's because I was thinking about multiplying 1.5 multiplied by 1.5. Then and after that multiply by 10, I thought it was different than multiplying everything in any order. But
which it's not.
Yeah, exactly.
So this is the commutative. This relationship here is something important for maths in general.
Yeah.
It's called the commutative property. And this works for multiplication. It works for addition. It doesn't work for division, for example. If you divide two things and then divide it by another, it's not the same as divide. The order matters for division, and I think the order matters for subtraction, but I can't remember now off the top of my head. But anyway, so yeah, this is true. So anyway, coming back to this is what we have, right? And this, if you think here, this is 0 going all the way to what? Our value over here, which is n.
Yeah.
Yeah, d theta n. So what we have is actually the sum from I equals 0 to n.
Yeah.
With d theta I.
Exactly.
Yeah? Now, if you look at this here, you can actually factorize this so that it becomes d theta 0 plus theta 1 plus theta 2 plus all the way up to theta n minus 1 plus theta n, right?
Yeah, you're correct.
But actually, this is the sum of theta
n
I equals 0 to n.
Yeah.
So you can just multiply. You can just multiply d like that. So let's write that. Let's write that again on a new piece of paper. So we are interested in a time t, which is
equals t.
which is dictated by the following function, which takes theta, d, and n. And that function is dictated by the following relationship, which is d sum of I equals 0 to n theta to the power of I.
Yeah.
Okay, cool. Now we have more or less our idea, right? For how we have a formula for how we can calculate this time t for the batch put reach way. So I'm going to cheat now. We have some inspiration from a formula, which I'm going to show you. Now, bear with me. I'm going to get a little bit sidetracked. Do you remember there is an identity, I believe, which is a squared minus b squared is equal to something.
No. So
a squared minus b squared can actually be factorized into two things, right? And what they are a minus b, a plus b.
Can't remember that, but okay.
So yeah, I couldn't remember it either, but it's true, and we can prove it, right? Because we multiply this one by that one, and then this one by that one, right? So it becomes a squared plus ab, and then minus ba minus b squared. These two cancel out.
Yeah.
So what do you have?
Yeah, exactly.
A squared minus b squared. Cool. There's another relationship which is similar to this, which is what? A to the n minus b to the n is equal to a minus b, a
plus b.
No, it's not a plus b because it's to the n.
Okay.
So this is where I came a bit unstuck. So actually, this here is actually a to squared multiplied by b to the 0, right? And this is a to the 1 multiplied by b to the 1, b to the 1, b to the a to the 0. So in the same way, this is actually a to the n minus 1. Because here, look, this here is n minus 1, right? A to the n minus 1 multiplied by b to the 0. A to the n minus 2 multiplied by b to the 1. All the way
and so
to
on at n.
Up to a to the 0 plus
to 0,
b,
yeah.
or multiplied by b to the n minus 1. Now,
okay, now I'm a bit confused.
yeah, so let me look up if I have this identity. But what this means, what you see here is a formula where this is actually a minus b is the sum from I equals 0 to n minus 1.
Mm-hmm.
This is still a n minus bn, where it's a to the I multiplied by b to the n minus 1 minus I.
Mm-hmm. Okay, makes sense now.
And now, what do we see? If we put this on the other side, we can actually rearrange so that we have yeah. So if we put this guy on the other side, we get this. So I equals 0, n minus 1, ai
b
to the b n minus 1 minus I is equal to a to the n minus b to the n all over to the b. Cool. So we can use this now to get rid of this guy. We have a formula for this sum. This series here, this power series, we now have a way of working it out, because we can use this formula here. So let's substitute that back in. So note there's something important here, which is here we have n minus 1, whereas here we have some...
I can see. Sorry.
Yeah, so here we have to the n, whereas here we have to the n minus 1. So we're going to have to shift everything when we move it. So when we do this, so what we can say then, when we put here I equals 0 to theta, so theta I to the n.
Yeah.
When we equate this, we're going to have to increment the numbers on here, because we have m plus 1. So we have one more. So this should be n minus 1 over here. Oh, sorry, this should be n plus 1 when we're going to have something like a to the n plus 1 minus b to the n plus 1 a minus b. Do you see why?
No, actually.
Because here...
Okay,
first of all, we'll come back to this in a second. But first of all, we need to match up these two equations. Now, the trick here is to say b is equal to 1. Why? Because that means that we can set a is equal to theta, and b has no effect, because it doesn't matter what I here is. It will always be multiplied by b to the something, over here, but this
I can see.
B is always 1, so it will just be removed, right?
I can see you, Pepe.
Oh, you can't see.
Yeah.
Oh, sorry.
Okay.
So yeah, so since B is 1, this term here
you're
is
correct.
removed. Removed. So we can use theta up here. Now we've got this. Now we need to substitute it back in. So what we can say is I equals 0, where theta to the I to the n minus 1, because here it's n minus 1, so we have to copy that, right? Is equal to theta, because here A is theta. A is theta to the n.
I can't see now.
Sorry. So is that better up here? Yeah, that's better. Just need to make sure you can see. So A to the n. Here we have theta to the n minus 1 to the n over theta minus 1. Now, if you look back into this equation over here, what we're after is up to n, not up to n minus 1. So if we do from 0, if we do the sum up to n, theta I, it's going to be theta n plus 1 minus 1 n plus 1 over theta minus 1. Correct?
Yeah, I guess so.
Okay, and now this guy we can put back into our original formula, which was T equals F theta dn, which equals d sum I equals 0 to n theta I. And then here we can replace this whole bit, so it becomes d multiplied by theta n plus 1 minus 1 n plus 1 theta minus 1. And that should give us the time that the function will take to run. And obviously this we don't need because of that. And the dominating here term here is d multiplied by theta to the n plus 1. Yeah. That's an approximation of what's going to happen.
Over theta, isn't? You don't need to divide. Okay.
Sorry, this is just a just an approximation, but this is the accurate answer. But yeah, so that's what I had planned for today. Yeah,
it's quite a while that I don't study any maths, so I'm a little bit rusty on that.
Me too. But it's good, right, to challenge yourself a little bit.
Yeah, sure.
All right, Jay. I've got to eat some lunch. Let's get on with the back on with the app. Thanks for today.
Okay.
And I really enjoyed it.
Yeah, me too. Talk to you later.
Cool.
Sorry. Bye-bye.